Can everyone see the screen
I can.
in Florida?
You see this kid?
Yep, yeah, good.
You're good, okay. So I'm trying to pick up with the example we left off on. And I really wanted, I know I said on Wednesday that the mathematics gets pretty complicated. Ultimately, we're going to be using software that has this all built in, and we'll go through some of that. WECA has it built in, and we can see how we can use it. But at some underlying, you should get some idea of what's going on underneath the hood, so to speak. So we were looking at this example on Wednesday. I think this is about where we left off. We had 8 instances in our training set. 4 of them were male, 4 of them were female. We had different, our attributes were height, weight, and foot size in inches. And what we're going to try to do is create models of the 2 different classes. So from the height, weight, and foot size, we should be able to distinguish whether a particular instance is male or female. And that's the idea here. And so what we did is, the assumption we'll use for this data is a continuous distribution, that the data comes from a normal distribution, a bell curve. In this case, we're going to end up with 2 different bell curves, one for the male samples, the male training set, and the female class. And we want to use that to try to classify the sample coming in the instance in the training set. So when we do this, we ended up with different means for the heights in the 2 different classes. The average height for males, 5.855 feet, females, 5.4 feet. Different variances, mean, weight averages, and weight variances again. And same with the foot size. And we're going to put those into our model along with the information from our test sample. So the values we have for our sample, what we're going to try to predict is the sex or gender of that individual given the height, weight, and foot size. So I just want to go back to that example. I know that the underlying probabilities got probably pretty heavy, and here I hope to make things a little clearer. The basic idea, and I'm not going to go through these formulas in detail here, but is we want to calculate their updated probabilities given the training set and now our new sample, what it would be our updated or posterior probabilities for male and for female. And the key idea here is we don't need to worry about the denominator. We're just going to calculate the numerator there. So I'm going to go to the next slide here. Did I skip? I must have skipped 5 or 6 slides here. So here are the calculations. So the probability of male, we assume it's an equal split in the population in general, 50% female, 50% male. Now, so if we notice here, I'm going to calculate, given that you're a male, we're going to calculate the probability of having the height, and in this sample, we had a height of 6, right? 6 feet, which is fairly tall. And on the right-hand side here, all we have is the formula, or the equation for the normal distribution, the bell curve. It's basically 1 over 2 pi times the variance, or square root of 2 pi times the variance, at e2 negative, and here we have 6 minus 5.855 quantity squared. The 6 is the value of 6 feet from our sample, and we're seeing how far away that is from the mean for being male, which was 5.855 feet. And the density function, the function is given by, in this case, x minus the mean squared in the exponential here, over twice the variance. And we're using the values for the male because we're looking for what's the probability that we have a height of 6 feet if we're assuming that the class is male. Okay? And we're going to do the same thing for the probability of weight being that you're a male. So we're again going to use our weight value, our average weight values and our variance for weight in our function here with our sample weight of 130. Okay? And if you can see kind of the symmetry in the equations there, is that coming together? And we do the same thing for the foot size. We get the values, the average values for the foot size for male, and as well as the actual value from our sample, which was an 8-inch foot size. And the average value was 11.25. The 0.91667 is the variance of foot size. And all we're doing is we're plugging those into into the general form for the bell curve. Pablo, you had a question?
We get a probability for the height, given that it's male, of 1.57. I thought the probabilities were supposed to be in between 0 and 1.
Okay, good question. Technically, if we wanted if we actually wanted the probability, we would divide by the probability of obtaining the actual evidence that we had. And that was the point I made in the last couple of slides, which I kind of skipped over a little bit. Because that value of dividing by the probability of the evidence is the same for calculating the probability of the height given female or the height given male. What I'm really caring about in reality is the numerator.
Okay, so what does the numerator tell us?
So what I'm looking for, I'm kind of doing a short circuit here, because otherwise you would have to calculate the evidence, probability of the actual evidence, divide by it. That would reduce that 1.5789. All of these numbers would then be numbers between 0 and 1 and multiply. But when I do the same calculations, probability of height given female, probability of weight given female, we're going to divide by that same denominator and again multiply. What I'm looking for is which probability is higher. And since the denominator is the same in all of the probabilities, I can just multiply the numerators and worry about which one is larger.
Okay.
So it's kind of a cheat here. I'll be straight on that.
Okay.
Excellent question. Any questions in Florida? No? Okay. So, and then this number posterior of the numerator, and so that's where I'm emphasizing, I'm really only looking at the numerator. These actually aren't probabilities.
Right.
The numerator here is 6 times 10 to the negative 9 is our value.
And that, what is the posterior numerator? Is that all of those?
That's these three, well, it's probability of male times, is all of these numbers, 0.5 times 1.5789 times 5.9 times 10 to the negative 6 times 1.3 times 10 to the negative third, multiplied together.
Okay, so the posterior numerators,
Is all of these numbers here multiplied together.
and then those are what you compare.
That's what we're going to compare.
Okay.
Yeah, we're good.
James, Katie, Drew,
I'm good.
James.
I understand when the numbers.
That's why I wanted to go through the example. And the other thing that I wanted to emphasize on this naive Bayes example, we're multiplying all of these numbers together. And all of that fancy talk that I was talking about on Wednesday about independence assumptions just has to do with that I just multiply those numbers together. I don't worry about interactions. What's the relationship between height and weight? What's the relationship between foot size and weight? Do those more complicated dependencies come into play here? On the naive Bayes approach, we simplify and say, no, we're not going to worry about that. We're just going to assume that height and weight are completely independent of each other, although we know that there's a relationship there. So I just want to emphasize that a lot of the fancy talk that I talked about dependencies and all that, comes down to, look, I'm going to treat height, weight, and foot size just completely separately. Just worry about those independently and do the straight multiplication there. And so now I do exactly the same calculations, except I'm going to replace my average height with the height for being female, or FW male.
Still got the probability of being male.
Right, so, and we get a different, and if you notice, right, because if you're 6 foot tall, the sample's 6 foot, it was much closer to being a male characteristic than a female. And we notice that just going back, it was 1.5789 in the first case, and now that's reduced to 0.22. But the other characteristics of weight of 130, much more characteristic. In fact, it's almost spot on for the average weight of the female class. It was quite a bit off. I think the average weight for the male class was 176 or something along those lines. So this number, 0.01, is significantly higher than the corresponding case for the male of 6 times 10 to the negative 6. And similarly, the foot size, 8 inches, was much closer to the sample or the training set's foot size for women than it was for men. So again, this the number that we get in the numerator for that characteristic is also higher than the corresponding number for the males. Throwing everything together, again, multiplying all 4 of these numbers together,
Yes.
Yeah.
0.5 assumed. That female.
Same problem.
we get 5 times 10 to the negative 4, and we compare that to 6 times 10 to the negative 9. So which class is it more likely to be considered? So, right, the posterior numerator, because the denominators are exactly the same, is significantly, in this case, greater for being classified as female than for being classified as male. So that particular example, we will now classify as female. And then you would go through the rest of your training set, different values, do all those individual calculations. Again, we did not calculate that denominator, which is a normalizing constant, to actually throw the numbers into the probability range, 0 to 1. It wasn't needed. All we needed was the numerators. So I want to leave it there, and possibly now go into the next topic, somewhat related, called Bayesian nets. But before I do, I just want to make sure, did the example make things come together more clearly?
Yes.
In terms of, there is some heavy-duty math in the background, but we're trying to really simplify it. And naive Bayes, we're making some incredibly some pretty broad simplifying assumptions, right? The attributes are independent of each other, and the class is separately dependent on each of those attributes, and not using more complicated dependencies.
So is that because of the naive Bayesian method?
That's the naive Bayesian method. This one thing that we will see over and over in data mining, or in general in machine learning, it's a very simple algorithm because of that. Despite the simplicity, and despite some of those rather large simplifying assumptions, it works surprisingly well. It's oftentimes better than more complicated methods, more complicated approaches. And that's one of the things that seems to happen a lot in data mining, is the simple methods. Quick and simple methods can sometimes be as good or even superior to methods that are much more complex, maybe try to include a lot more things, but you end up losing something along the way.
Okay, so if we were trying to find a correlation between the attributes and then compare them between male and female, we could end up with
Possibly worse results, right?
okay.
It kind of comes down, in a sense, to that trying to do things as simply as possible, but no simpler than necessary. Occam's razor. The experience has shown that sometimes the simplest methods work surprisingly well. I mean, that's kind of the upshot of that. The next, we're in this whole module of classification. We've gone through a number of classifier types now: decision trees, rule-based classifiers, and we're in the midst of Bayesian classifiers. We talk about naive Bayes. There's a whole nother class that also works quite well, Bayesian networks. And one of the pioneers of Bayesian networks was a computer scientist back in the and mostly in the 80s and 90s, Judea Pearl, he's at the Cognitive Systems Lab at UCLA. A really good book he published. He was kind of one of the real forces behind promoting probabilistic methods for machine learning and data mining. He authored this book in 1988, Probabilistic Reasoning in Intelligent Systems. We're going to begin with it. We're going to look at an example, a simple example that he considered there. He was also, Daniel Pearl was his son. And he was a journalist. He worked he was on assignment in Pakistan in 2002 for the Wall Street Journal. I remember hearing about this, and he had been captured and was decapitated by Al Qaeda in 2002.
Did we catch him?
Yes. The murderer was, I forget the murderer's name, the actual person who did it, but he was brought to justice. So that's an aside, so Bayesian networks is in a broad class of classifiers, or broadcast of network, class of networks. It's what's called a probabilistic graphical model. We'll see why, because we're actually going to see the graph here. And the idea here is we're going to let our random variables and all our probabilities and conditional dependencies, we're going to view these using is everyone familiar with a directed acyclic graph?
Sure.
Yeah, I don't know what you're talking about.
Okay. Often referred to as a DAG. Well, I'll show you a picture.
Can I have an example?
I'll show you a picture of
Is
a
that the
directed
same thing
acyclic graph.
Is that
It's-
like a diagram?
A digraph, yes, a digraph is a directed graph, right?
Okay, yeah.
An acyclic means it does not have cycles.
Okay.
So let's see if I have, well, let me move to the picture. Here's a picture of the example we're going to use. This is a DAG.
Oh, I've seen this. Okay.
Okay, it's directed because there are arrows.
Yeah, there are.
There's no cycle here.
Right. Okay.
The arrows don't make a circle, a cycle.
Question.
Could a DAG be like the stuff we did last year in mathematical thought? Like that,
I didn't teach
I
mathematical
know, but
thought.
that web thing we did where you directed the webs, the five.
That was a diagram, so as long as it doesn't make a circle.
As long as it
You're
doesn't
right.
make a cycle.
That's what he just
You already
said.
did the
And
class.
then you just asked a question that he already answered.
Please continue, sir.
Thank you, Pablo.
Ours is more advanced.
Okay, so this is an example of a directed, the arrows. You've got the nodes, which here are represented by circles. The edges are represented by the arrows here, and there are no cycles that occur. If you follow the arrows, they all end up in grass being wet. And we'll come to this example because Pablo's like, what is this about? So, the edges, those arrows that we were looking at, represent conditional dependencies. Going back to that picture, we're going to have, and notice I'm going to have tables here, we're going to have, if it rains, then that arrow is saying, now we have, there is a probability that the sprinkler will come on. That's a conditional dependency. It depends on whether it rains or not. That's what I mean by a conditional dependency. The probability of the sprinkler comes on depends on whether it rains or not. If nodes are unconnected by an edge, then we think of them as conditionally independent, that they don't have a dependency, that it's just, they're completely independent. And they do not all the attributes. So unlike the case of naive Bayes, now we can start to have some conditional dependencies. So height and weight can be related and dependent on each other. The taller you are, typically the more you're going to weigh. And then that might impact the probabilities of being male and female. And the picture again is going to really give a lot here, right? Because we're going to have probability tables associating each node to its immediate parent nodes. And so I've listed here, if a node doesn't have parents, is everyone familiar with a parent node? Something pointing into it, a node that points into it, then the probability is just the probability of whatever that node represents. Whereas if you have an arrow pointing from parent to its child, the table is going to represent, as we see again on this page. So if we look at rain, rain has no parent. There's nothing directed into rain.
If you had cloud into rain.
If you had cloud into rain, and there's another example of this example where we actually have another node, cloud, up here, pointing to rain and sprinkler. But I wanted to try to use the simplest example that we can. So the rain node, this is just your regular probability. The probability it's going to rain. End of discussion. Probability is 0.2, it's going to rain, and probability, therefore, 0.8, it won't. And that's given by that table up in the right. Now, notice sprinkler has, so rain can be either true or false down this column here. And then you've got a probability of different probabilities of whether your sprinkler comes on or not. So if it rains, there's a very small chance that the sprinkler will come on, a 0.01. And meaning that if it rains, there's a large likelihood the sprinkler won't come on. But if it doesn't rain, the false here, there's for whatever reason only a 0.4 probability of the sprinkler coming on and a 0.6 of it not coming on. Maybe you want it water every couple of days, not every day, right? Then we look at the bottom, grass wet, and notice for grass wet we actually have two arrows pointing in, one coming from rain and one coming in from sprinkler. And so what that means is we have four possibilities of the combination of sprinkler and rain. So sprinkler could be false or true, but at the same time rain could be false or true, so that gives false, 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 true, true, false, or true, true as our inputs into grass wet.
Wait, so isn't that grass going to be right either way?
Well, it's going to be, if If it doesn't rain and the sprinkler doesn't come on, the grass won't get wet.
Well, I thought if it doesn't rain, then the sprinklers will turn on.
They've got a probability associated with it. That's this table here.
Okay.
If it doesn't rain, the sprinkler comes on sometimes, but not all the time. Comes on 40% of the time.
Okay.
So if neither of those happen, well, the grass won't get wet. If it rains, but the sprinkler doesn't come on, because if it rains, the sprinkler still can come on, maybe it doesn't rain hard enough, right? So the grass wet is dependent not just on whether it rains or whether the sprinkler comes on, but it's dependent on both of those events. So this is a little more complex than what we looked at in the naive Bayes method, where everything was completely separated. I think that actually, yeah, I think that covers that. So this model that we now create, and it's going to depend on, and we're going to see how this works if we have time, if not today, on Monday, when we actually bring up WECA and start looking at how this is implemented there. The model is going to encode the relevant probabilities, and then we can use those probabilities to start making inferences. And the first thing we want to do, there's this concept of a joint probability. And in this example, the joint probability we're going to construct is a probability table for all three events. So the grass is, it's going to be all the possibilities of the grass being wet or not wet. The sprinkler coming on or not coming on. It raining or not raining. So ultimately this would be a table of 8 possibilities with the corresponding probabilities. The probabilities we can think of this way, let's go back to the graph. So we can think of is the probability of, is it going to rain, times the probability that the sprinkler comes on given that it rains, or the probability it doesn't come on. So, and then, so that's the first 2 terms on the right-hand side here, probability that it rains, the probability that the sprinkler comes on given that it rains, and then finally, the probability that the grass is wet given the combination of whether it rained or not and whether the sprinkler came on or not. So you end up with 8 different probabilities of whether the grass is wet for all of those. So here's where, again, we can start making more complex, and I hope I made this relatively clear. We can again now say your observation. You come home from being away for a little bit, and you notice that the grass is wet. So again, notice this reversal process. We're going to try to use Bayes' theorem, which we talked about on Wednesday, to say, okay, I notice now, right, the graph here tells us if it rained, what's the probability of the grass being wet? If the sprinkler came on or not, what's the probability of the grass being wet? If the combination came on, we can figure out what the probability of the grass being wet is. But now, in this next problem, we want to reverse that process and say, look, I come home, the grass is wet. What's the probability that it rained? I don't know whether the grass being wet came about because it rained, or whether the sprinkler came on, or whether both happened.
So recursion.
Not recursion, Bayes' theorem. And so I'll go through, so is the setup fairly clear here? And again, we'll see it with probably the weather example, going back to that one, in WECA. So here's how it would work. We want to know, look, we know the grass is wet. Can I figure out what the chance is that it rained? So that's what this first statement on the left says. Probability is raining, given that, that's the vertical line, the grass is wet. And so that is given by, well, I know the grass is wet, so that's always in my denominator. I'm going to normalize by that probability that the grass is wet, because I know that's what happened. And the way that it would also be raining would be on the numerator is the probability that both happened. It's raining, it rained, if we're looking at the past tense, and the grass is wet. So what fraction of the time that the grass is wet did it also rain? So that's really what we're looking at here. And in the next line here, and probably clearer even on the next slide, but we're going to sum over all the possibilities of the sprinkler being true or false. So the grass can be wet when the sprinkler is on and it rained, or the grass can be wet when the sprinkler was off and it was rain. That would encompass both cases for it is raining and the grass is wet. Now, if I look at just the grass is wet, what are all the possibilities? Well, I could get grass wet when it's raining and the sprinkler came on. We can get the grass wet when it is raining and the sprinkler does not come on. We can get the grass is wet when it doesn't rain and the sprinkler comes on. Actually, one case that should not appear, and I make this more clear on the next slide, is that, well, here I actually have all four cases. The other possibility is that it neither rained nor the sprinkler came on, but the grass is still wet. And that's basically what this slide is encompassing. And if you notice, I gave here a probability of 0 to if it's raining. If it didn't rain, because that was in our table, if it didn't rain and the sprinkler didn't come on, there's no chance of the grass being wet. So hopefully this makes it a little clearer. And notice I'm looking here at the two cases in the numerator. 0.1, I did the calculations, or actually I got these. 0.198 plus 0.154, which also appear in the bottom. It's the fraction of the time that it's raining, and so this is the 0.198 comes from the rain. It's raining, and the sprinkler is on, and the grass is wet. And the other possibility is raining, the sprinkler is off and the grass is wet. So remember, the numerator had raining and wet. So I look at both of those cases, sprinkler on, sprinkler off. In the denominator, I want only grass wet. And so the grass wet, is that what I? What was the denominator, grass being wet? Yeah. So I look at all the possibilities of the grass being wet. There was a chance of it raining, sprinkler on, grass wet, raining, sprinkler off, grass wet, raining. Did I get all the cases?
Yeah.
Okay.
Yeah.
So, oops, I may have gone. Okay, so I want to talk a little bit more about Bayesian networks in general. So, how does one actually develop these? And so it's a two-step process. One process is we have to create the actual network structure. What is the DAG, the directed acyclic graph that we're interested in, actually look like? What are the dependencies? And then the second part of that is we actually have to determine the probability values of the tables. The simplest approach is so on an example like this, you create the network by hand, right? We have raining and sprinkler and grass wet. But if you're looking at more real world type cases, the world of what the network can look like gets too complex too quickly, and we're going to have use some machine learning algorithms to determine the network. And we'll talk about that by looking at how all of this works in Weka, and we'll do that on Monday.
Monday.
So there are a number of algorithms, so this is kind of the transition to where we're going. On Monday we'll actually look at how to use Weka for implementing Bayes nets, and some other tools as well. In Weka you can build in your own user-defined network. There's an algorithm based on what are called conditional independence tests, evolutionary algorithm genetic search. So these are classes of algorithms that we can set up. A hill climber method, which is basically looking for the most probable case. It's climbing the hill to get to the most probable case. An algorithm that we'll look at in maybe a little detail is K2.
Ooh, I like K2.
Simulated annealing, that's the default. K2 is the default in Bayes network, in Weka. Simulated annealing based on annealing, for example, of metals in physics, so it kind of mimics that idea. And then a couple others, maximum weight, spanning tree, and taboo search. And there are a number of other versions of BayesNet software available online. I'm going to just mention one. It's a toolbox for MATLAB, developed by Kevin Murphy at the University of British Columbia, along with his students. And there, you do a search for BayesNet's tree and you'll find that link pretty quickly. So on Monday, we'll begin looking at how to use Weka for doing some of these other
I think you want the icon right above the share. You want it out of full screen.
So I think that wraps it up for today, and then on Monday we'll actually go back in and how to get Weka to do a lot of this for us so we don't have to really necessarily understand all those details inside.
Yeah.
So questions?
Nah, we great.
Florida?
Yeah. That's good.